Mhm.
So in this question, which is related to binomial, you're asked to consider 1 minus x to the power of n times 1 plus x to the power of n equals 1 minus x squared all to the power of n, and then show that for a integer value of r, this expression is true. So a few things here. Firstly, you're given sort of binomials, and you're given an identity, which is very nice, but also very standard in a 3-unit paper, or even 4-unit for that matter, to be given an identity and say, consider this, show something. Now, when you're asked to show something, as we discussed, there's mainly two types of problems, what we call type 1, where one side is an algebraic identity, or type 2, where the other side has a sort of combination. Here you can clearly see there's a combination of NCR, so this strongly suggests it's a type 2 question, which we pretty much say our strategy is to compare coefficients of some power of x. So that's where we're heading. We don't know what that power is at the moment without a little bit more work, but we know we're likely to be comparing coefficients of some power as opposed to subbing in values for x. Now, to be able to progress further, we really want to have an idea of both what we're trying to prove as well as what identity we're using. So I would suggest that when you have a column across this, you write out each expansion in binomial terms. So 1 minus x to the power of n is the sum from a counter. Because I've already used k, I'm going to deliberately pick another letter. So let's say L equals 0 to n of NCL negative x to the L. And that will just be L equals 0 to n of NCL negative 1 to the L x to the L. Okay. Now, just to save ourselves a little bit of space, I'm going to get rid of that working and move that across. Now, this is great, and it's nice and compact, but if you don't understand what that's actually saying, then it may be helpful, even in an exam scenario, to spend a little bit of time to write out what that actually means, because if you're not comfortable with singular notation, that doesn't help. You actually need to know what this is actually saying. So what this is saying, of course, is I'm going to go from L equals 0, okay? And I'm going to go to L equals 1, I'm going to get L equals 2, I'm going to go dot, 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 to L equals some number, right? We'll just say L equals L as an example. And then lastly, to L equals N. And we're going to add each one of these together. So when L equals 0, you sub in 0, that's NC0, negative 1 to the power of 0, x power of 0. So it's going to be NC0, negative 1 to the 0, x power of 0. This will be NC1, negative 1 to the power of 1, x power of 1. This is going to be NC2, negative 1 to the 2, x to the 2, and so on and so on and so on. So in general, we're adding up a whole bunch of NCLs, negative 1 to the L, x to the L. And of course, NCN, negative 1 to the N, x to the N. In other words, we're saying it's 1 plus NC1, which is N, times negative x, plus NC2 x squared, plus dot, 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 plus NCN, negative 1 to the N, x to the N. In other words, we're saying it's 1 minus NC1x plus NC2x squared minus NC3x cubed plus NC4x power 4 minus NC5x power 5, etc. That's basically the pattern we're saying. Does that make sense?
Mhm.
Okay. Giving us the space. We're going to move that. So if you are comfortable with the sigma notation, you don't need to write this out. This writing this out is really just to give you a sense of what's happening here.
Yeah.
Of course, we want to also do the same thing for 1 plus x to the power of n. I'm going to pick a different letter. We've already used L, they've already used K, so we'll use M. So it's going to be NCM x to the m, just using a binomial theorem. And you can do the same thing as before, just expand it out. Hopefully, just following the steps that we did earlier, it will be fairly easy to understand that this is going to be 1 plus nc1x plus nc2x squared plus nc3x cubed plus, well, nc4x power 4 plus dot 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 plus, well, ncn x to n. All right. So those are the two expansions that are left. We also want to expand this one. And so I'll pick p this time. So from p from 0 to n of ncp negative x squared to the p. So that, of course, would be the sum from p equals 0 to n of ncp negative 1 to the p x squared to the power of p, which you can then use your index laws to get x to the power of 2p. And so that would be the simplified version. Now, due to the lack of space, I'll just go directly to write out what this represents. But basically, we're going to sub in p equals 0 first. So that's going to be nc0. Negative 1 to the power of 0 is 1. X to the power of 0 is, again, 1. So this is still 1. Because you've got a negative 1 to the power of 1, when I sub p, now I'm going to sub p equals 1 now. So it's going to be nc1, negative 1 to the power of 1, so minus nc1, x to the power of 2 times 1, so it's x squared. And then I'm going to sub p equals 2, so that will become plus nc2 x to the power of 4, because when I sub p equals 2, that's power 4. I'm going to have minus nc3 x to the power of 6 plus nc4 x to the power of 8, dot, 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 dot. So this will keep going. Now, of course, this can't actually go up that high, because if you look at it, well, actually you can, because it's power n and power n. So it's important to understand what these represent, but it's quite cumbersome to write these out all the time. So if you understand the sigma notation, you can use that. But now, basically, with a little bit of minimizing here, we're now basically saying through our work that considering the identity, we're now able to say when we take L equals 0 to the power of n times NCL, negative 1 to the L x to L. So that is this part. I'm now going to multiply it by this part. So that's going to be the sum from m equals 0 to n ncm x to n. Of course, that just represents the entire thing here as well. So there's a whole bunch of terms. And that equals this on the right, which we understand is the sum from p equals 0 to n of ncp negative 1 to the p x to the 2p. So we've now used binomial theorem to change this expression into their respective expressions in binomial theorem. Now we just want to remember this is our aim. We want to prove this. Now remember our strategy. Our strategy is to compare coefficients of some power of x. So if you do a comparison with this side, this is a negative 1 to the power of r NCR. If you want that to be a coefficient of some power of x, this side is just going to have a whole bunch of products of NC something times NC something. That's going to be on the left-hand side here. So to get us our idea of what power of x we want to compare, we want to focus on this side. You'll notice this is negative 1 to the power of r NCR. Has to come from here. So we want negative 1 to the power of r. So we want this to be r. And you want x, like you want that to be r, right? So because you want negative 1 to the power of r NCR, that basically means by comparison, we want P to equal R. And if I want P to equal R, that means it's x to the power of 2R. So we are trying to compare the coefficients of x to the power of 2R. That's how we would do this question. So now it's clear. We need to use this to get the coefficient of x to the power of 2r on the left-hand side, because the coefficient of x to the power of 2r on the right-hand side is this. As long as we can prove the coefficient of x to the power of 2r on the left-hand side is this, then it's true. Okay, so this is x to the power of 2r. We now need coefficient of x to the power of 2r on the left-hand side. Now we do need to, of course, copy out what we have. So we've got the sum from NCL negative 1. Okay, so we don't really care too much on the right-hand side, but for completeness, we'll write it in. Just double check everything is correct. Okay, looks fine. So remember, we need to compare coefficients of 2r. So that means for the left-hand side, remember you're taking every term. So remember what this is, right? Remember this is a whole bunch of terms. And remember this is a whole bunch of terms. You're trying to take this blue bracket and you're multiplying by this green bracket, which means you're going to have every one of these terms times every one of those terms. So you're going to get, well, n plus 1 terms times n plus 1 terms, giving you a n plus 1 squared number of products, many of which will have like terms, but you'll get lots of them. We don't need to care about all of them. We only need to care about the ones that give us x to the power of 2r. So you're going to think about how you're going to get that x to the power of 2r, and you basically take the power of x of the term you're multiplying by times the power of x. Now, for a particular term, it's going to have the power x to the L. The Lth term will have that power, and the mth term will have that power. And when you multiply them together, you're going to get the power of x to the L times x to the m is equal to x to the L plus m. And we want that to be 2r. So we require L plus m equals 2r. Now, that then means we need to consider all the possibilities of getting L and M within their ranges to become 2R. And you literally just run through them. So L could be 0, the lowest L. If L is 0, then M has to be 2R. If L is 1, then M must be 2R minus 1. If L is 2, then it must be 2R minus 2. And this obviously keeps going on. If L is k, if L is some number k, then M must be 2R minus k to make that up. And then, of course, at the very end, L can get to 2R and M can go to 0. So you can see that basically L starts at 0, M starts at 2R, L goes up by 1, M goes down by 1. End of story. Okay, so that would cover every single possibility that L and M could add together to give 2R, and therefore that covers all the possibilities out of all M plus 1 squared possibilities that you're going to get the power you need. So now you need to then work out the coefficients. Well, the coefficient of the L is just going to be subbing in that. So that's going to be -1 to the 0, NC0. It's going to be -1 to the 1, NC1. It's going to be -1 to the 2, NC2. Dot, 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 dot. So it's going to be -1 to the K, NCK. And it's going to be -1 to the 2R, which is just going to be positive, of course, NC2R. And we can simplify this down a bit. This is going to be positive NC0. This is going to be negative NC1. This will be positive NC2. And this will be unknown because we don't know what K is. That's the coefficient from the L. We also need a coefficient from M. Well, that is simply going to be NC2R, NC2R minus 1. There's no negative this time. NC2R minus 2. Dot, NC2R minus K, and NC0. So you've worked out the coefficient from the L. You've worked out the coefficient of the M. Now, of course, when you actually multiply two things together, the coefficients also multiply together, which means your coefficient will just be these two things multiplied together. So you're going to get NC0, NC2R, minus NC1, NC2R minus 1, NC2, NC2R minus 2, -1 to the K, NCK, NC2R minus K, NC2R times NC0. So this is your overall coefficient of each term. But of course, all of these have the same x to the 2r. So this is, all of them will be x to the 2r, x to the 2r, x to the 2r, dot, dot. So when we actually want the total coefficient of x to the 2r with all of these, we then need to collect like terms. So we then need to sum these up. If we were to sum these up, then basically, if you compare against, if you try to write this in sigma form, you're basically just taking all of these times all of those. So in other words, the sum could be written as -1 to the K NCK, NC2R minus K, where K goes from 0 to 2R. And if you compare, we've got the K equals 0 to 2R, -1 to the K, NCK, NC2 minus K. Therefore, we have proven that these two are equal. So now we want to hence. It's probably always best to consider what you're using. So remember, we're trying to show this. We don't want to use this. And so you really want to focus on any sort of similarities that you can find between what you know you have to use and what you want to prove. Now, things may not match exactly, but you want to have an eye out for anything that appears related. And what might be of interest is that this seems to be -1 to the K, NCK, NC2R minus K. This appears to be the same. Now, of course, this is 0 to R, and this is 0 to 2R. So they're not exactly the same, but certainly the terms inside are the same. So that would suggest that I might tackle the problem starting from the left-hand side. And the left-hand side is, well, I might start tackling the problem, I suppose, using the left-hand side of this. This is 0 to 2r. Now, I'm going to force this in. And that's pretty easy, because if I'm just going from 0 to r, and the inside's the same, I could go from 0 to r of this. And then I still have things left. That I'm left with everything from r to 2r, r plus 1 to 2r. I'm not finished, right? I'm meant to go from 0 to 2r. I went all the way from 0 to r, but I need to keep going from r plus 1 to 2r. So this is the same thing. I've just split it into 2 bits now. Now, I know this is -1 to the r NCR. So you can see you've got that thing there. So this part is what they want. Okay. This part is not. We're going to have to deal with this part somehow. So this part we won't touch because, well, why would we? That's literally what we want. We know that the left-hand side is equal to -1 to the r NCR, so we know that. So we need to simplify this somehow. So if we're going to go from r plus 1 to 2r, let us see if there's anything we can do about that. Now, if we just write out a few terms here, that might help. So that means we've got -1 to the r plus 1, NCR plus 1, NC2r minus r plus 1, plus n minus 1 to the r plus 2, NCR plus 2, NC2r minus r plus 2, plus dot, 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 and ultimately you're going to get -1 to the 2r, NC2r, NC2r minus 2r. So hopefully a pattern can be seen to be forming here. We've got NCR plus 1. We've got NC2r minus r. So that's r minus 1. Plus -1 to the r plus 2. NCR plus 2. And that's going to be NCR minus 2. Plus -1 to the 2r, NC2r times NC0. If you let this be m equals 0, you can think of this as 2r minus m, where m is 0. And that will just be even numbers, so that's going to be +1. Basically, I'm saying that this is the same thing as that, except it's missing one term, right? You've got the 0 term here. You've got the 1 term over here. You've got the 2 term, 3 term, 4 term, 5 term, 6 term, 7 term. You've got everything up to, well, the r plus r minus 2, the r minus 1 term. In other words, I'm saying this is the whole thing. Minus 1 term, which is you've got everything from 0 to r minus 1. I'm saying it's that, okay? I'm saying that these two are equal if I go from 0 to r minus 1. And I'm not interested in going from 0 to r minus 1, so I need to think of this as from 0 to r minus the rth term, which is -1 to the r, NCR, NC 2r minus r. In other words, this thing we're trying to simplify is equal to this minus that. Okay, so this part that we're simplifying on the next page is equal to the sum from k equals 0 to r, -1 to the k, nck, nc2r minus k, minus, well, the rth term. And if you do a comparison of what this is the yellow thing as well. In other words, we're going to have 2 times the yellow thing minus that. Now, 2r minus r is just NCR. So, what do we have? The left-hand side was this, but that's just equal to -1 to the r NCR. So therefore, we've got -1 to the r NCR equals 2 times the yellow, which is what we're trying to work out, minus -1 to the r NCR all squared. All we need to do now is rearrange to make yellow the subject. Okay? So move this across. So in other words, you'll have -1 to the r NCR plus -1 to the r NCR squared equals 2 times the yellow. You can then factor out the -1 to the r, which gives you this part. You can factor out the NCR, which gives you 1 plus that. So if we factor out -1 to the r NCR, you're left with 1 plus NCR. And that's 2 times the yellow. From here, it should be very clear that the yellow, which is what we're trying to prove here, is simply divide the two across, half -1 to the power of r NCR 1 plus NCR as required. Does that make sense?
Yeah.
You can see there's a lot of sort of algebra manipulation here.
So basically, we need to know that there's only like one middle term, and then the other parts are the same.
There's not one middle. Well, I mean, we just split it up. It was from 0 to 2r. We split it up from 0 to r, and then from r plus 1 to 2r. Now we were missing something, so we added it back to get to. We wanted to force in the yellow. Otherwise, we had a big mess to deal with. Right?
Yeah.
The last part, then again says hence evaluate for 1 mark. So this should be much easier. So this question asks us to hence evaluate this sum as a basic numeral, considering, of course, that we already have the things we have above. This should be significantly easier. So keep in mind, in part 2, you already have this expression. So you already have this expression, and you're just now saying, hence, work that out as a basic numeral. So you just need to do a bit of matchup. K equals 0, excellent. This is 6, that suggests r is 6. -1 to the k, excellent. 12ck squared, well, if r is 6, right, then this suggests that, well, your n is 12. All right, so you've got n is 12. Now, if r is 6, then you've got, that's 12, right? So if you just play matchup, you've got the sum from k equals 0 to 6 of -1 to the k, 12ck, 12c 2r, which is 12 minus k, must equal half -1 to the r, n, which is 12, c, r, which is 6, 1 plus ncr. So we know that's true. You're asked to evaluate from k equals 0 to 6 of -1 to the k, 12ck all squared. All right, well, the thing is this. You should also know that ncr equals ncn minus r. So that's just an expression you should know from your combinatorics. So this is, the left-hand side is the sum from k equals 0 to 6 of -1 to the k, 12ck all squared. Because 12c, 12 minus k is 12ck by this expression. And therefore, it must equal this on the right. Half, -1 to the power of 6 is just 1. 12c6 times 1 plus 12c6. Put that in your calculator. And you get an answer of 427,350. And that's it. That's how you do it.